These are your introduction notes on gases, the nature of gases, real versus ideal gases, and the kinetic molecular theory. So gases are made of independently moving particles. These particles move in random directions at varying speeds until they collide with another particle or a barrier. Gases have no definite volume or shape. We remember that from our first unit where we reviewed our properties of matter. And the gas laws pertain to what we call an ideal gas, which is an imaginary gas that serves as a model for gas behavior. So we'll talk about the difference between a real versus an ideal gas in just a minute. So conditions for an ideal gas. So an ideal gas is an imaginary gas that fits all of the assumptions of the kinetic molecular theory, or the KMT. Real gases are particles that have size and intermolecular attraction to other particles. So thinking London dispersion, hydrogen bonding, dipole-dipole bonding, those kinds of things. So that's an intermolecular attraction. So they do not conform, real gases do not conform to the gas laws under very high pressure or very low temperatures. The reason why they don't conform to gas laws under very high pressure is because particles under very high pressure are forced together and are attracted, thus are not considered ideal. Under very low temperatures, gases are moving so slowly that those molecules could interact and have some attraction. So again, under very high pressure and very low temperatures, real gases do not act like ideal gases. And these are the reasons why. Again, at high pressure, the molecules are forced together and they force an attraction, and at low temperature the molecules don't move very fast and thus will have a chance for an attraction, and thus it's not considered an ideal gas. The kinetic theory is based on the idea that particles are always in motion. We know that nothing in nature is ever stagnant or stationary. And so we know that with gases, they're always moving. So at the same temperature, all gases have the same kinetic energy. But gases do not have the same speed. So for example, we know that kinetic energy equals 1/2 mass times volume squared. So velocity squared, sorry. Mass is m and velocity is v squared. So if we were looking at this order of elements and compounds, if we wanted to rearrange it from the fastest to the slowest, basically what we need to do is look at the mass. So I know that the smaller molecules are going to move faster. And a real life example of thinking about this is who would run faster, a 350-pound football player or a 120-pound runner. Okay, just think about that smaller molecules are going to be a little bit faster moving. Here's an example of that, smaller molecules moving a little bit faster. All this is an example. You don't need to be expected to do the math. It's just walking you through it. So all gases have at the same temperature have the same kinetic energy. So if the kinetic energy is -20, the speed for the gases would be different, even though the kinetic energy is the same. The speed would be different. And so and the velocity would be different. Okay, so there's just a math example of that. So theories of the kinetic molecular theory assumptions. So the first one is that gases consist of a large number of tiny molecules that are far apart relative to their size. They have a low density and a lot of empty space between the particles. There are a lot of elastic collisions. They don't stick together after collisions, so there's no net loss of kinetic energy. At high pressure and low temperature, gases are not considered ideal because the collisions are not elastic. So that's one kind of way that we can compare real versus ideal gases, is that there's not an elastic collision at high pressure or low temperature. There's no attraction or repulsion for an ideal gas, so ideal gases do not condense into a liquid or solid because there's no attraction. Real gases, however, do condense. So for example, carbon dioxide condenses into dry ice, or we can have nitrogen condense into a liquid. We know that kinetic energy is the energy of motion, so gas particles, again, are in constant motion, and that's a very rapid motion. The kinetic energy is the energy of motion, and the average kinetic energy depends on the temperature of the gas. So the faster the molecule is moving, you assume that it's at a higher temperature. Gases, we know, expand to fit the container, so there's no definite shape or volume. Gases are fluid, so they slide past each other. The fluid as attractive forces are not significant in a gas. They are very significant in a liquid and a solid, which will be our next unit. Gases have a very low density because the particles are far apart, and gases are compressible, so particles can be pressed close together. Liquids and solids are not compressible, so that's something to kind of compare. Diffusion, so gases can diffuse. This is the random mixing caused by random motion. So the rate of diffusion depends on temperature, size, and attractive forces. So temperature, thinking like about a candle, okay, small molecules will move faster, and attractive forces. So if it doesn't have an attractive force, it's smaller. So there's two ways to look at if something will move faster. So if I compare oxygen and water, okay, if I'm looking at the speed in terms of if it moves faster based on polarity, we know that oxygen is a nonpolar molecule and water is a polar molecule, and so the polar molecule will have more attractive forces on it. Thus, I would say if I'm looking just at polarity, oxygen would move faster. If I'm looking at size, we know that water is 18 grams and oxygen is 32 grams, so water would be faster because it's smaller. I would never ask you to compare these two in terms of which would move faster because we don't have a way to test in our lab on whether or not which would move faster based on size or polarity right now, and so I would never ask that comparison question. I would ask based on size which one would move faster or based on polarity. So please don't worry about having to compare the two. Gases also effuse, which is under pressure. They can pass through tiny openings. So obviously the smaller the molecule, the faster the effusion. And this is one of the reasons why a balloon does not stay full forever, because molecules, helium or oxygen or carbon dioxide, will effuse through tiny openings in the balloon. So just a question here, will helium or carbon dioxide balloon deflate faster? And we would assume a helium balloon would deflate faster because it's a smaller molecule and can move faster. So there's your notes, slides 1 through 13 on the nature of gases, real versus ideal gases, and the kinetic molecular theory.